Hey there. It's been a while. Been busy with other things, primarily work, but I received a question sometime around Christmas, sometime in December, I believe, to do a video on the binomial option pricing model. Pretty straightforward. At least the conceptual part of it is sometimes dealing with the bookkeeping and indices and relating nodes, different nodes in the tree to each other. Bit of a pain, but yeah. Without further ado, let's just get into a notebook and get after it. Okay, so notebook. I did a bit of recording, and then all of a sudden the audio went wonky. So I'm just going to kind of re-record this. We didn't really get that far into it, so it's not that big of a deal. In terms of imports, we're just going to need NumPy basically, and to store these tree structures, since Python doesn't have a native tree data structure. I know there are libraries that implement them. But instead of using those, I'm just going to use a sparse matrix here to store these data. Matplotlib just is for diagnostic purposes, and I don't know if I'm going to use it or not, but I am going to bring in the Bernoulli distribution function as well. So these are the two tree structures we're going to look at. So this is the one that we really want to understand. Once you get this, going on to more complicated things is basically the obvious extension of this simple model here. And a bit of nomenclature. I think I'm going to call like this first level the 0th level, then the next one the first, then the next one after that the second. So if you come down to this tree, this would be 0. This would be like the first layer, second layer, third layer, fourth layer. That's just to keep the nomenclature consistent with the way Python does indexing of matrices. So the idea is simple. You start off with some stock price, which we'll call S0. So let's just define that down here, and we'll just set it equal to $100. So S0 is equal to 100. Some time step later, we'll take that to be 1 year. So let's just explicitly put that in here. T is equal to 1. You either go up by some percentage U with probability P, or down by some percentage D with probability 1 minus P. So let's come down here again, and let's make U equal to like 5%, so 1.05. This is equal to U. So the price in this node would be, it's 5% above this, so it's 1.05 times S0. And let's take D to be the reciprocal of that. So D is equal to 1 over U, and it looks like I forgot an equal sign here. Okay, and doing it this way makes this more complicated trees a little more simple. So for example, if you are at this node here, for example, and you go down by an amount D, you'll end up here, and that's the same as starting here and going up by the amount U. And this is kind of a reflection of the log normal distribution of stock prices. I mean, there's an equal percentage chance of going up by a factor, going up by 100%, or going down by 50%. So in other words, the probability of the stock doubling is the same as the probability of the stock being cut in half. And for the sake of argument, let's just say the probability of going up is, I don't know, let's do it 60%. So P is equal to 0.6, and obviously 1 minus P is 0.4. So this enables us to calculate both of these, whatever you want to call this. I call them SU and SD down here, and I gave them numerical indices down here. But so let's just say S sub U is equal to U times S naught. And likewise, S sub D is equal to D times S naught. So one thing I don't know if I said explicitly is this time T is basically the time until expiration. So this last column here, or likewise the last column here, is at option expiration. And well, at expiration, it's easy to figure out the value of the option at these particular nodes. If the option is in the money, it's just whatever intrinsic value it has. And obviously, if it's out of the money, there is no intrinsic value. The option is worthless. So Let us restrict ourselves for the time being to call options. Then the intrinsic value is just the stock price minus the strike price. So let's figure out what these two stock prices are, just so we can kind of choose a reasonable strike price here. So let's print S S underscore U and S underscore D. So 105 and roughly speaking 95 and change. So let's set a strike price of, I don't know, let's do K is equal to 102.5. And eventually we're going to need the risk-free rate, so let's just do it 1% annual. So the call price at expiration for SU, let's call that CU. Well, that's in the money, so C underscore U is equal to S underscore U minus K. And C underscore D, that'll be the call at this node D, is, well, it's out of the money, so that's equal to 0. So now we have everything we need to do to back out the price of the call at our initial time. And I think what I'm going to do is just come up here and I'm going to type out the formula and then basically describe how it comes about. So here is the formula. The price of the call at one node back is equal to, well, let's go to this term first. It's P, our probability of going up, times the price of the up call, the call at this point, plus 1 minus P, which is the probability of going down, times the value of the call at this downward node. So this term here that's in the parentheses is basically the expected value of the call. It's essentially, if you did a Monte Carlo simulation with these probabilities, it's the average value you'd get for the call option. And then what we do is we just discount it by the risk-free rate, since some time has passed, there's some upward drift assumed, and that basically backs out the risk-free rate. So that is it. And now we can just come down here and use these numbers here to estimate the price of this call option. So let's come down here. We will say, what will we say? C is equal to np.exp minus r times t. That gets multiplied by p times c underscore u plus 1 minus p times c underscore d. And close parenthesis, that should be it, print c. And that is not right. Mistake in the formula. That looks good. 0. That should be SU. That's the problem. S underscore U. Let's run it. And that makes a lot more sense right there. So the extension to this is obvious, at least conceptually. If you have the price at expiration, you could just back out the price of any of these individual nodes. Once you have the price at these individual nodes, you can back out these and, you know, just backtrack until you get to your original call price. The only complexity is basically just bookkeeping and then making sure you scale all the individual quantities correctly. Because the time now is not exactly 1 year, it's 1 year divided by whatever these individual time steps. Well, if this whole range from like start to end is 1 year, this might be, 3 months, 6 months, 9 months, 1 year. So you have to take into account that you're taking 3-month time steps rather than the full 1 year. So let's come down here and make up some values and just kind of try to code up something like this. So for the time being, I'm going to set the number of layers basically equal to what I've sketched out on the screen here. So I'm going to say n is equal to 5. I'm going to say t is initially equal to 1 year, the total length here. So the time step is going to be equal to t is equal to t divided by n minus 1. No typos. So just as before, let's set our initial stock price as 0 is equal to 100. We'll take the risk-free rate again, being equal to 1%. And instead of just kind of hard coding U and D, what I'm going to do is assume we know a volatility sigma. I don't know what we should set this to. How about 40%? And then U and D is just going to be basically equal to a scaled version of that volatility. So U is equal to np.exp sigma times the square root of time. So it's np.sqrt of t. And then U is obviously the reciprocal of that 1 over D. And that's going to be equal to CSC matrix. And our size is going to be n by n. And we're going to have a call matrix or call prices that's also equal to the same type of thing. It's an empty CSC matrix, size n by n. Looks good. Any typos? Apparently not. So, I don't know quite how to do this. Let me set our initial stock price as 0. We already did that, but let's put it into this matrix. And then let me code up let me write the code that does the propagation throughout all these nodes, and then I'll go back and explain how we're doing the bookkeeping here. So I'm going to set this equal to stock prices, and it's the 0, 0 node. Okay. So here's the code to propagate forward those prices. So we are starting, it's two nested loops. Our outer loop here, our main loop goes from here. You notice it starts at range 1 to n. So we're going from here out to here. And then we're doing a loop over a second index, which I called M. And M is going to go basically from bottom to top. So if you're out, if I is equal to 1, 2, M is going to go from 0, 1 to, from here to here. And then we put them into the corresponding values of our stock price matrix. I think it'll be easier to visualize that. So let me just run that again, make sure it's all good. And then the reason I pulled in the matplotlib library is so we could visualize what that matrix looks like. So plt dot spy, which is a very useful command, by the way, stock prices. It's a useful command if you're actually populating a matrix with anything other than 0. So let me see if I can figure out where the problem is here. Oh, I think I see where the issue is. I think when I set this, I essentially reset the stock prices to 0. So let me set this equal to S0 and delete this kind of thing out here. That should do it. That looks better. So this kind of shows how the bookkeeping is done. As we move down this matrix, or up in matrix index, we are moving from right to left across our tree here. And as we're moving right, from left to right, we are moving from the bottom to the top here. And then everything is just shifted over because it's a square matrix. And that's kind of why I use the sparse matrix. I don't think it's really that important because all the other values we're not going to use in the matrix itself because they're going to be 0. What we could do is just kind of, let's just bump this up to like, I don't know, 50. So you get this type of shape here where you're only using half of the, if you were to allocate a full dense matrix, you'd be using twice the amount of memory. So probably not really that big of a savings, but you know, I just figured I'd do it anyways. So let me get rid of this for the time being, and now let's do the same type of loop for the call prices. So it's just basically, you know, now that we know all the stock prices, we can just go back off and populate the matrix of call prices. So let's do that here. So at expiration, so let's create a variable just called expiration. These will be the call prices at expiration. And now it's a little bit of a pain because we have a vector here. So what I'm going to do is the following. I'm going to say the value at expiration is equal to the stock price minus the strike price. The issue there, print expiration. The issue there is that it doesn't handle the out of the money option, so we get these negative strike prices. And for some reason, we're getting a let's just reshape that vector. So expiration dot shape is equal to expiration dot size. I don't know why it's coming back as like a two-dimensional array. So I just kind of reshaped it just to, I don't know why, just to make it a little cleaner looking. So we need to handle these out of the money options. So I'm going to use the np.where command and just basically replace any of the negative values with zeros. So I'm going to do that up here. So this should work. I should really test it out before recording the video. So we're going to look for the expiration values that are greater than 0, and we're going to keep those, and then we're going to replace the ones that are less than or equal to 0. Let me make this less than or equal to with 0. So, and then I print out the new vector. So let's just see if that works. Yay, it actually does. So let's get rid of the print statement now, and call prices. We'll just set that last. We'll set the corresponding last row of that matrix, which is -1, and all the columns equal to that expiration vector. So let me. Oops. Glad I caught that now because I would be looking for typos for ages. Does it run? Yes, it does. So let's actually do a spy on this call prices matrix now. So it should only be the last row. And indeed it was. And if you remember that print statement, which I unfortunately deleted, these other three values were also 0. So we only have these two populated with something that will appear in our spy matrix. So I'm going to do something similar to what I did up here and just kind of write the code and then talk through it, because again, it's a lot of just bookkeeping type of stuff. So let's do it down here. Okay, so the bookkeeping is similar to the way we did this. We just kind of do it in reverse order. So instead of from going 1 to n, we go from basically n all the way back to 0. So we're starting here and going back. And then we're going basically up the loop again. Where am I here? We're going up the loop, up the columns of this tree structure here. So we're going basically up this way, and for whatever value we're at, we look at the index above and below it in the column that's to the right, and then we just implement our call value function. So let us see if this actually gives us a reasonable answer. Looks good as far as SPY goes, so let's print out the call prices 0, 0. Does work better if you spell print correctly. So there we go. $3.33 is the value of our call at time equal to 0. So the value of the call at this point here. Okay, you may have noticed that the price here changed, and I was going to say, and I was doing this off of the recording, that the number of layers you basically use, it should converge very rapidly to a single price. And I was changing this number n off of screen, and the price kept going up and up and up and up, and there was obviously something wrong. That turned out to be a typo here, so I fixed this. I had written u is equal to 1 over d, so it was picking up this d from up here and then screwing up all the probability. So that's fixed. And another change I made is the code was running very slow. And if you recall, there were warning messages that rearranging sparse matrices is inefficient. So I just made these dense matrices of zeros, and now it runs reasonably well, at least fast enough for this type of demonstration. So with 5 nodes, we get a price of 14.7. I don't know, let's just go to 500 nodes. We get basically 15 point, 15 point something, so it's basically the same, so it converges pretty quickly. So let's just go, I don't know, how about 51 nodes? 15.2, so it converges within, not too many layers. So I'm going to set this back to 5, and that is about it. So cool. Pretty straightforward. At least conceptually, it's pretty easy. The issue is generally the bookkeeping. At least that's where I struggle with these kind of things where you have multiple loops and indices that you have to kind of adjust the positions thereof. So yeah, as usual, I will clean up this notebook, put it up on GitHub, and yeah, cool. I will see you later.